It's a great pleasure to be here. For those of you who don't know me, I'm relatively new to the country, and so today, I was very excited to have the opportunity to come and tell you about some of the work that we've been doing, focused on sustainable iron catalysis. But hopefully, really what I want to show you today is how we approach the types of problems we encounter in some of these reactions, the type of physical inorganic approach we take to solving them. And in so doing, defining really unprecedented organoiron chemistry that would make it very challenging to understand reactivity de novo, because many of the structures I'll show you today would get you failed in an undergraduate exam, basically. But they do exist, right? So I use the title chemical synthesis in advertising the talk, so you'd all still show up. But as I mentioned, in reality, we look at organic reactions. And our interest in iron, there are many reasons for this. Some of them you would all know. There's a lot of iron. I love to plot transition metal availability in a pie chart because I think sometimes in the logarithmic charts, it gets lost about how much iron there truly is in the world, how there's a tremendous amount of titanium. You got some more 3Ds and you wouldn't see the 4 and 5D metals on this plot. Also, from geopolitical reasons, unlike palladium, iron is pretty much everywhere. You can find a rusted out car pretty much anywhere around the world. But what we're really interested in a metal like iron for organic synthesis is driven by kind of two other things. One is toxicity, right? So if we're going to do organic transformations, we're going to do a lot of applications in pharmaceutical synthesis where it's not just cost and sustainability, but toxicity of residual metals. You may have to go through very complicated and costly measures to separate. And so if you look at the European Medicines Agency ratings for metals from the most recent update, iron's not even listed. It's effectively a vitamin. Whereas metals like cobalt, which my group also enjoys cobalt chemistry, are actually considered more toxic than many of the precious metals one would look at. And then lastly, iron's not palladium, right? And I hope to show you today that's absolutely true. That means there's going to be opportunities for novel and complementary reactivities that are not currently accessible with more traditional precious metal catalysis. And so all of these things really motivate us and many others in the field to try to push this field of iron catalysis as far as we can for applications in synthesis. Now, if we're going to use iron for organic transformations, just to remind all of you who wanted to forget your organic chemistry for the last 30 years, that means we care about basically making carbon-carbon bonds, carbon-nitrogen bonds, carbon-oxygen bonds, maybe a carbon-sulfur bond, and breaking CH and CC bonds. And if we're going to use iron in a practical way, synthetically, we're going to need to be able to do this across many different classes of reactions. So today I'll tell you a bit about things like cross-coupling and CH activation and hydrofunctionalization catalysis, but there are many, many different examples, and this slide is by no means exhaustive. Now, as you might guess, I'm a big believer in the future of iron catalysis, and so it always pains me to show the next slide, which is to say that iron simply isn't very good. Okay, if I was going to run a catalytic reaction, perhaps even in an academic lab, certainly at larger scale, I too would probably still turn to palladium catalysis. There's much more that's been done in these reactions. They're very reliable, they're very predictable. We understand them very well mechanistically, and that enables rational design of new catalysts and new reactive applications. And so if we want to get iron to a point where it can be competitive, we really need to be able to overcome all the issues that iron catalyzed reactions have, and there are many of them. First and foremost, there hasn't been a lot of reaction development done in iron catalysis, certainly not by comparison to metals like palladium or even nowadays nickel catalysis. Second, and probably most painfully, is it's not uncommon to take a really cheap metal like iron and put a Ferrari costing ligand on it, which at least certainly defeats the entire purpose with respect to cost and some sustainability options. So if we want to use iron, we want to also be able to figure out ways to use it with relatively simple, tunable modular ligands. And there are many other challenges as well. Now, the problem is these are really hard to solve in iron catalysis because for most of the reactions that have been developed, we don't understand even what is the resting state of catalysis, what is the nuclearity of the resting state in catalysis, what are the natures of the key catalytic steps that are involved in reaction. And so this kind of lack of mechanistic insight has really been a challenge for rational development. Like, for example, I loved Donna's talk. If I had to draw a mechanism doing kinetics on some of the iron reactions, I wouldn't even know what to draw around the iron, which is why many people draw iron in brackets, which is by far the most commonly proposed iron intermediate in organic chemistry. And what I hope to show you today is that
you can solve these problems. They're not unsolvable. They're challenging. But when you do so, the types of insights you get really open up kind of the black box of iron catalysis and enable us to rationally design new ligand classes and new reactions. Wrong one. So full disclosure, I was trained as a bioinorganic spectroscopist, about as far away from organic synthesis as you can get. But in bioinorganic chemistry, there are a lot of iron-containing enzymes where one wants to study the active sites, mechanisms, and so on. And these have similar challenges to the types of questions we might have in organic synthesis. And so our group takes a very physical inorganic approach to understanding in situ formed iron speciation, reactivity, and so on, where at the heart of it are a lot of very physical inorganic techniques. So one of the nice things of moving to the UK from the US is I brought 3 iron Mossbauer spectrometers with me, which we have in Oxford now, magnetic circular diaprism. We do a lot of EPR and so on and so forth. And so by combining these types of methods, we can really study in situ using freeze trap time resolve type methods, the types of iron speciation we're observing. We can assign those through really challenging crystallography. So we're actually, I worked in industry as well at Dow Chemical for a while, where I learned some engineering from my engineering friends. So we have things like liquid nitrogen directly into glove box, all kinds of custom cold plates, so we can handle really unstable intermediates. And of course, that's the inorganic side of the equation. We have to connect this to reactivity, products, kinetics, and so forth. And we do this in many different systems. So we kind of face studying iron catalyzed reactions, what I like to term as 2 different kind of classes of challenges. Now, the first one is, I think, the one everyone would immediately think of with homogeneous catalysis. I have a well-defined iron complex with a well-defined ligand attached to it, or I have an iron salt combined with something that is obviously a ligand, right, like a bisphosphate. I put it in, I do a reaction, and some ligands work, some ligands don't work, right? There's all kinds of interesting effects. And so trying to understand what are kind of structure-activity relationships that enable catalysis across classes of ligands and classes of reactions. In some ways, this is the easier problem to solve mechanistically. Not to say that anything with open shell iron catalysis is easy, but we've worked in this area for many years. And I'm not going to go through any detailed examples today, but just to say, if we're looking at, for example, just iron bisphosphine compounds in cross-coupling reactions, you can look at how, for example, in an aryl alkyl cross-coupling, you might use a very bulky, what's called a SIOP bisphosphine, whereas when you go to an alkyl cross-coupling, it only works with sandphos. Right? And what are the origins of these? And if you define how these reactions work mechanistically, and these are all reactions that involve a combination of 1 and 2 electron steps and radical intermediates, you can then develop reactions that you can't do, let's say, with traditional palladium chemistry, such as the 3-component radical cascades that we've done together with my good friend and colleague, Osvaldo Gutierrez. What I thought would be more interesting to this group than telling you the newest and latest and greatest thing we've done in ligand-based reactions is to focus on a different type of problem, and a problem that reminds me of my time doing heterogeneous catalysis at Dow, which is really what I like to call witches, brews, and magical potions. This is so that the students in the audience don't forget it. But the reality is I'm a card-carrying inorganic chemist, and I would love to stand up here and tell you that molecular inorganic chemists make the best iron catalyst for organic reactions, and I would be lying to you. The best reactions that have typically been developed, defining best as best product yields, best productivities per unit time, are typically developed through basically a trial and error mechanism where you add salts, you add additives, which we might call promoters, right? You add various types of solvents and things that it's not quite clear what they're doing at a molecular level, but the catalysis works. The problem is, how do you make it work better? How do you address substrates that don't work if you have no idea what you've made? And so we find these both intellectually interesting, but also, I think, kind of at the forefront of trying to understand how to move the field forward. So that's what I want to focus on today, is how do we address these types of challenges? We are basically in situ making what is almost a mess of compounds. How do we sort them apart? How do we decide and identify resting states? How do we identify reaction pathways? How do we identify what something's doing? And is it always the same across all reactions? And I'll show you that the answer to that is not always yes. So what I want to focus on today is, I think, a subclass of these, which are ones that we like to think of in terms of having reaction additives. So to give you an example of what I might classify as an additive, we can go back to kind of the history of iron catalyzed cross-coupling reactions where basically you can do all kinds of couplings and very high atom efficiencies, so long as you add N-methylpyrrolidone as a co-solvent. If you do not add it as a co-solvent, reactions don't work very well. You need a lot of excess Grignard. It's very atom inefficient. What is its role in catalysis, right? I think it's an interesting question. And every time I tend to give this talk, I like to give you a second to think about what you think it might be doing in catalysis. I could certainly come up with a list of more than 1 or 2 or 3 things. But this is what I mean by the challenge of additives. It is clear that the use of N-methylpyrrolidone is essential to high catalytic yields, but its molecular role in affecting practical catalysis is ambiguous. Right? And so really, I also like to, for fun, just say, how does the magic happen, right? What is going on at a molecular level that enables this catalysis? And in the case of N-methylpyrrolidone, we really need to know this because this works great, and it's a horrible reproductive toxin, right? So you do not want to use this in any type of pharmaceutical applications. And so if you could define how it works, perhaps you can circumvent that. There are many others of these as well. One of my favorite ones is this example from Noshell, where you add isoquinoline to the reaction as an additive, and now you can do an aryl coupling. Use pyridine, doesn't work. Get rid of the isoquinoline, doesn't work, right? And so this is one we're currently working on. Tamida, which I'll talk a lot about today, is one of the most common additives. You might immediately tell me that's a ligand. And I would say it probably is a ligand, but a ligand to what? Is it on cycle? Is it off cycle? Is it actively promoting catalysis? Is it preventing catalyst deactivation, right? And this additive works across all kinds of classes of reactions, which makes it very imperative to understand. It's also a very cheap additive, and hence makes it very attractive. And of course, even things like alkoxides that you might put in, you might say, well, that's obviously a base, right? Or an activated boronate. I completely agree with you. What will it do to an iron compound is an interesting question when it's in excess at 60 degrees, right? And so again, trying to understand how these work is essential to really moving the field forward to higher performing catalysts. So just to give you an example of the N-methylpyrrolidone kind of quickly, really this N-methylpyrrolidone reaction of Kaye is a modern version of what is really one of the first metal catalyzed cross-coupling reactions, predating palladium and nickel by a few years, by J. Kochi in Indiana, where you just take a simple iron salt, about as cheap as you can get, nucleophile, electrophile. We would call this Kamada coupling now, but Kamada hadn't found its reaction yet, right? So at the time this was reported, and you can get very high yields. Now, this reaction looks great until I tell you that you need a huge excess of nucleophile for this to work. The electrophile scope is not particularly broad, right? There are a lot of challenges. But if you simply take this reaction, add N-methylpyrrolidone, you now can do atom-efficient reactions. You can now do whole classes of electrophiles, halides, pseudohalides, and so forth. And the conditions might look different, but trust me, you can run this at 0 degrees, and it's done in 5 minutes. And you can run this with iron chloride. It works just as well. Actually, the most common issue we run into is a reaction is reported to take 12 hours, and the first thing is, well, how long does it actually take? Oh, it takes 30 minutes. Okay, well, we kind of need to know that before we do the kinetics. So many of these reactions are actually even faster. And that highlights another challenge, right, we're going to have. These are fast reactions, right? These things are turning over, in many cases, 100 times in 5 minutes at 0 degrees. So we're clearly dealing with relatively low reaction barriers and relatively unstable intermediates. So many years ago, we looked at the Kochi reaction. I'm not going to talk about it in detail other than to maybe attract the attention of a HEPCAT person in the audience who would like to use an 8 iron 12 methyl complex as a precursor for putting small pockets of iron metal in a compound. Obviously, you put this on the surface, it reduces to metal and gives off ethane. But this is what does catalysis in the Kochi system, okay? And this is a perfect example of a compound that even with all the spectrometers we have, we would never have gotten the structure, okay? So what does NMP do? Well, the first thing I should tell you is that cluster, unsurprisingly, is quite brown, right? The solution is dark brown. And if I do the exact same reaction where I would make the cluster, but now add NMP, I get a bright yellow solution, not brown. And we can look at what the iron speciation is by using freeze-trapped Mossbauer spectroscopy. Now, I know the audience isn't full of Mossbauer aficionados, but simply to say that first, The salt has to be enriched with iron 57 so that we can look at it at catalytic concentrations on the millimolar scale. Second, you have to have liquid nitrogen in your glove box in order to do the trapping, but we've engineered all of that away. And third, each unique iron species we're going to look at today, because we're doing non-magnetic Mossbauer, is going to be this kind of vampire fang doublet. So the important thing, I'm not going to go into all the details of Mossbauer, but each unique iron species has unique doublet. And the integrated areas are roughly proportional to the amounts in solution. So you don't have to be an expert to say, I'm making mostly one thing. Okay? It's not EPR active. You can run EPR. EPR is far too sensitive. It looks like a beautiful spectrum. It is. That's what's in the baseline. This is a teeny tiny amount of cluster, and this is a little bit of an iron 3 tetramethyl we've independently made. So it makes one thing. So what is it? Well, now for those who thought about what NMP might do, it's iron 2 with 3 methyls on it. All the NMPs go to the cation. You make these tris methyl ferrates. You might say they're very unstable. It depends on how you define unstable. It lives at 0 degrees in solution for about 10 minutes, reacts in about 3 seconds, right, with electrophile and makes product. You might also ask the question very reasonably, how do you know that was in solution? You simply crystallized it. Well, fortunately, we have a lot of spectrometers, right? And so we can run Mossbauer on the isolated crystals, which perfectly matches what was in solution. We can do things like MCD, which is, for the purpose of today, an advanced absorption method that looks at metal center transitions, and that matches what's in solution as well. And so we can perfectly correlate isolated intermediates from solution samples. This way, even though this thing is horribly paramagnetic, it's spin of 2. You can run NMR of it. We have reviewers, those we're doing reviewer comments, who always want us to run NMRs of, well, also EA, but NMRs of things that die at 0 degrees. The EA will always pass as long as you don't make a gaseous product. This one will not pass because it makes a gaseous product when it dies. But the NMR is a slight blob at about 0.5. Okay. The methyls are simply too close to the iron. And so we do a lot of NMR. It's incredibly useful, but there are going to be compounds where it simply is not. Now, NMP, as I mentioned, isn't a great additive. And so a good friend and colleague, Guillaume Lefebvre in Paris, working with Caillet, figured out that they could use alkoxides instead of NMP, right, as additives and do the same reactions. Does it do the same thing? Yes. Without going into all the details, it makes iron trimethyl, just like we did before. It's equally reactive as it was before. It's just much less stable. So by changing the cation, in this case, the alkoxides go to the cation instead of the NMPs, this rapidly decomposes to cluster. And so you can do comparative experiments. You use the same excess of both alkoxide and NMP. You always make more trimethyl with NMP than you do alkoxide. It always lives longer before it decomposes, right? And so this works. It just doesn't work as well. And that really brings to kind of a broader challenge. We've looked at lots of these systems, different nucleophiles. We can crystallize, and we have structures of everything that's on the screen. But if you look at these catalysts simply, because these are kind of ligand-free systems, you can see that the ligands derive from the nucleophile, which means that every time I change the nucleophile, I change the catalyst, right? It either works, it doesn't work. There's not much I can do to tune reactivity in these systems. The reactivity is tied to the nucleophile. And so I had a very talented postdoc who had the idea, well, we only ever transfer one of the methyls, so why don't we replace 2 of them with a bisanomide ligand? And I'm not going to go through this because I know showing a slide of organic reactions makes everyone twitch a bit. It works, okay? And so this is just simply one example of how if you understand what is the fundamental structure of the iron catalyst that's responsible, no matter how bizarre it is, you can then utilize that insight to target specific ligand designs that target that type of core structure. And the nice thing now is once you get to this type of motif, you can start to think about making chiral ligands and doing enantioselective couplings, which we could never do with the Caillet or the Cauchy systems. But it's promised, I want to take the last, I think, 20 minutes that I have to focus on what I think is a more interesting set of reactions in many ways, which are these Tamida examples. So as I mentioned, with Tamida, you can do aryl-alkyl cross-couplings. You can do hydromagnesiation reactions, borylation reactions of alkyl halides. You can do CH functionalization reactions, lots of reactions. I could make an equally big slide with all of the TMDA reactions. Cobalt, this is a very, very common additive. And so a question we had in thinking about basically structure-activity relationships and iron catalysis is, what is TMDA doing in all these reactions, right? Sorry, I tend to use TMDA instead of TMDA. Is it always the same? Is it always a ligand to iron? Is it a ligand to something else? Is it on cycle? Is it off cycle? So on and so forth. And so to kind of highlight how challenging this is to think about, I want to turn to these cross-coupling reactions. So the original reaction by Nakamura in 2004 showed that if you use iron chloride with a large excess of timida, you could do these aryl-alkyl cross-couplings. And Janine Cossey and France showed that you could extend this to other couplings, as had Fox and Warwick. And so the question is, what are the key, reactive iron species that do catalysis in these reactions? But before doing so, I do want you to note two really important things, because process in these cases is as important as the nature of the additives. All these reactions always have large excess of timida in order to work. And what Grignard is always added slowly with a syringe pump. If you just chuck it all in, they don't work. Okay? And so these will be two important factors to take into consideration when trying to understand the role of timida. So there was quite a debate in the literature between two groups, and I actually think they're both perfectly correct, right? For the systems they were looking at, which is fun. So Nakamura himself, a few years after the original result, decided to try to understand if TMEDA iron aryl complexes could be responsible for cross-coupling activity. And so he made monomesotyl and bismesotyl complexes of TMEDA that could be isolated, structurally characterized, and he could show that the mono one could be transmetallated to the bis. The bis would react with electrophile and make product and go back to the mono. The mono does not react with electrophile. Now, you might say, why the mesotyl? Because trust me, that's not a very common aryl you might use. It's very practical. Iron aryl compounds are stable. They tend not to reductively eliminate. Iron phenyl compounds, not so stable, right? And so this was very much a practical choice for trying to get manageable compounds. And then a few years later, Robin Bedford at Bristol came along and did a beautiful set of experiments where basically showed, yes, I can make this same bis aryl, but if I add a little bit of extra Grignard to the reaction, all the TMEDA falls off and I make iron 2 tris mesotyl. Okay? And that this is very reactive. In fact, kinetically, it's more reactive than the TMEDA bis aryl. Also, the product distributions I get from using this in catalysis perfectly match, right? And so the argument was, okay, yes, a TMEDA iron aryl could do the chemistry, but for mesotyl, it's clearly a tris mesotyl species. Now, there are two interesting things to note immediately. First, mesotyl, remember, it's a model substrate. It's a terrible substrate in catalysis. So it only gives about 32% yield, where traditional phenols, or fluorophenols, so on and so forth, are all 90 plus, right? So really the model itself is not a very good catalyst, which does question whether it actually reflects a broader set of aryls. And second, there's no accounting for that slow addition of Grignard reagent that's essential. So for example, yes, this will react with more Grignard and get knocked off, but that only matters if it is added faster than it reacts, for example, right? It has to actually live long enough to be killed. So we decided to look at this, but with traditional aryls, right? And so just simple phenyl. Now, the first challenge we're going to have is, can we even make an iron phenyl complex, right? The whole reason you do mesotyl is because they're stable. If we take TMEDA iron dibromide and they have one equivalent of Grignard, we make one iron. Remember, again, a symmetrical doublet. That's one iron species. If we had two, we make a different one. The isomer shift goes down. That suggests more covalent ligation. They're actually not that unstable. So you can crystallize the monophenyl and the bisphenyl. It just took us forever to do it because they're colorless, and my student was convinced they were magnesium salts and just threw them away for 2 years. But once you know how to make them, they're actually very easy to get to. And so with those in hand, we also obviously now know what the parameters are for each of those compounds. So if we see them in frozen solutions, we can track them. We can also, of course, do the exact same types of experiments to start that Nakamura did. Are they even reactive? Do they react at initial rates that make any sense for catalysis? So if you take the monophenyl, it does not react. You take the bisphenol, it reacts very, very rapidly. And in fact, it will turn over more than once. This is the common telltale sign we've seen in many reactions for these type of radical cascades where we initiate a radical and then we can go around more than once. So certainly the bisphenol, just like the bismuthitol, reacts fast enough to make the correct product distribution. Also, the nice thing with Mossbauer's, I don't have to worry about copper having done the job for me. We can look directly by iron freeze trap Mossbauer's that yes, our bisphenol was definitely consumed and went to a series of TMEDA iron halides with and without THF on them. And the most important thing is reactivity. This reaction occurs with a rate that's greater than 6 per minute observed. The Grignard is added at 0.02 equivalents per minute. I told you slow addition is really, really important, right? So therefore, you would expect if I look in catalysis, I'm going to see basically a lot of TMEDA iron species. I never generate enough excess to knock it off. And that's exactly what we see. So actually, if we look in catalysis, it's all sitting there at the monophenol, right? Basically waiting to be transmetylated again. And all we see in catalysis are TMEDA ligated species. And so with mesoteals, which are much more donating and much more bulky, there's no doubt they knock off the TMEDA if you put in too much of it. I completely agree with that. But with less donating, less bulky aryls, actually, they tend not to knock off TMEDA at these large excesses. And so in this case, TMEDA is an on-cycle, or TMEDA ligated iron is an on-cycle species. So is TMEDA ligated iron always an on-cycle species? Well, another fun one in our exploration of TMEDA is this hydromagnesiation reaction we did a few years ago with Steve Thomas at Edinburgh. So basically what you're doing here is for those who've made Grignard reagents, you would normally just take an organohalide, treat it with magnesium metal, right, stir it up, and you're good to go. But there are some cases where it's challenging to get the organohalide precursors, or it's simply easier to make them from alkenes themselves. And so what Steve had found is you could take styrene derivatives, iron chloride, either a bisaminopyridine ligand or timida, and you could effectively make a new Grignard by sacrificing a beta hydrogen containing Grignard, in this case, ethyl Grignard. Now, what originally attracted us to this system wasn't the timida, it was the bisaminopyridine, because this is a telltale redox non-innocent ligand. So how can you do the same reaction with a redox non-innocent ligand and with a ligand that absolutely is not redox non-innocent, right? And we certainly looked at the redox non-innocent case, and the key resting state is an iron 0, formerly iron 0, A-1 ethyl, A-2 ethylene type of intermediate you can trap out, right? And you can crystallize these. But what about the timida system, right? And so we started off by doing what was a relatively simple experiment, which is let's just take iron dichloride with the excess timida. We'll add excess reagents, both the Grignard and the styrene. We'll drop the temperature to 10 degrees, which just slows everything down a bit for us. And what happens to iron is a function of time. So what you'll see is that 5 minutes into the reaction at -10, it's mostly one iron, which is actually a TMEDA iron bisethyl compound. We can also isolate that. Iron compounds don't tend to beta hydrogen eliminate as much as you might be familiar with palladium. And then over the course of 30 minutes, the speciation continues to evolve. And you can see that red kind of goes away and these orange and purple species come in, right? And so the orange and purple species we could also independently synthesize. And these are iron 0, alkyl tris eta-2 styrene compounds. They're actually spin of 1 iron 0. It's very unusual. They're monoanionic. I'm not showing you the cation. One of them has the ethyl on it, which is the sacrificial Grignard, and the other one has the product Grignard on it from the reaction. So basically these TMEDA iron 2s don't immediately reduce to iron paddle. They slowly reduce over the course of an hour into these styrene stabilized iron 0 alkyls. And what we could go on and show is that these types of iron 0 alkyls are really responsible for catalysis. So when we have at early time points all TMEDA iron ethyl around, we make no product. But as that is converted into the iron 0, we can now get catalytic turnover. You might say, why use a TMEDA at all, right? Just chuck it all in. If you do it all, it just craps down as iron powder. The TMEDA iron alkyl effectively slows down the reduction process, ensuring that in this case, all of the iron can get converted to these spin of 1 iron 0 alkyls, which are then effective for catalysis. Actually, even in that bisaminopyridine case, this pyridine eventually gets knocked off, and you make these same compounds as well. And these are actually really nice synthons now for accessing iron zero compound. And so that's an example of TMEDA is important for catalyst activation to access the correct oxidation state for catalysis, but the TMEDA is not on the iron during the catalytic cycle, right? So it's a second, slightly different role of TMEDA in these reactions. So for a third, even different role, I want to turn to some work we've done last year with Lutz Ackerman and Joanna Wenzel-Delord on some iron catalyzed CH activation catalysis. Now, our group has been interested in iron CH activation for many years, right? And I would say that historically there have been kind of two types of reactions for these. You can go down the iron zero bisphosphine kind of path, and these have been known for 40 years and do CH activation. They tend to get locked up at hydrides. Or you can do directed CH activation. And that's effectively what Lutz is doing here, where you have some type of moiety with, let's say in this case, a nitrogen donor ligand. Sometimes these are triazoles, sometimes these are quinolines that can bind to iron, orient the CH bond to the substrate such that it can now be CH activated. And most of these have been done with things like phenanthroline ligands and bisphosphine ligands using aryl Grignard reagents as the hydrogen acceptors. So the reason we were interested in this system is that this one is quite different. This one is not a bisphosphine. This one uses a chiral NHC ligand. It also, as you can see, uses a Grignard reagent and TMEDA. In order to achieve catalysis, you get rid of either of those. Catalysis does not work. And I'm not going to belabor the organic chemistry other than to say there's lots of really nice EEs on this slide, and the catalysis clearly works. We were more interested in how does this work mechanistically, and why do you need such a soup of reagents in order to get it to work? And so the first thing we did is we ran the catalytic reaction, and we proved that we could actually do organic chemistry and we could make the correct product yields and everything looked nice. And then, of course, we can do the same thing. We can do freeze trap spectroscopy during catalysis, both Mossbauer and EPR. I'm not showing the EPR because there's nothing in the EPR. It's a flat line. But in Mossbauer, it's mostly one iron species. Now, our group has done a lot of iron NHC studies for years, looking at detailed electronic structure studies, DFT, all kinds of spectroscopy. And these were not parameters that we recognize, right? And so, of course, you're stuck at this point within how do I identify this, right? We're never, I mean, we could try, but we're never going to crystallize this on a catalytic mixture. But we started to think a little bit about how this reaction might work. So Yoshikai himself had proposed a 0,2 site. Now, unfortunately, it's the iron in brackets again, which I mentioned shows up a lot. But what is the iron zero if it exists? What is its structure, and why do we need a mess to make it? And so we look back at the catalytic reaction, and this should look very familiar to you if I haven't put you to sleep yet, which is that in the hydromagnesiation reaction, you also use an iron salt, right? You use a beta hydrogen containing Grignard, and you use TMEDA, and you make those iron zero alkyls. Oh, wait, I also have styrenes, right? This is looking very familiar. And so we had the hypothesis that maybe all that's going on is that you need the TMEDA and the cyclohexyl Grignard to access one of these iron zero alkyl styrenes. Then, since the NHC is always added as a hydrochloride salt, you could protonate this off and simply make an iron zero NHC complex. So a controlled reduction to form an iron zero NHC. And I wouldn't be showing you this if it didn't work. We can make all of these compounds. We can crystallize them all just by the synthetic pathway I'm showing you. And the parameters of this through numerous methods, including Mossbauer, are exactly what's present during catalysis. Okay. And furthermore, we can go on and show that this is competent to react directly with the substrate to do CH activation and make product in a stoichiometric reaction. So this would be an example of TMEDA, again, helping with catalyst activation, but basically controlling reduction so that an iron compound can be sacrificed. And this is actually a really exciting synthetic pathway now for us in terms of accessing new classes of spin of one iron zeros for a variety of transformations, because you can envision all kinds of ligands you could introduce now at iron zero, going through these alkyl intermediates, or even making iron main group heterobimetallic. And we've done that as well through this type of synthetic pathway. So I know that was a bit quick, but hopefully I've given you a sense of the fact that some of the most interesting reactions in iron catalysis are really these kind of thrown together mixtures that reach some magical combination that is incredibly effective for catalysis. And that if one studies in detail what are the core types of iron species that one can access in these reactions, you discover a whole weird world of organoferrates and other types of compounds that are very effective for catalysis. I think the reason we never found them in organic chemistry is why would we make things that are unstable, right? But with a better understanding now of how these work and how additives work in catalysis, we can start to think about designing new ligands, testing new pre-catalysts to push transformations forward. And so with that, I'll just leave up the slide of the people who actually did the work, which is not me. I have a wonderful group of talented students, collaborators, and funders. And with that, I'd be happy to address any questions you have.